All right, so welcome everyone to the second ATiA seminar for the semester. It's my pleasure to introduce Tung Lam, who is a third-year PhD student here at UAlbany, and he's going to tell us about presentation-based metrics on merge trees. Just as a reminder, feel free to interrupt and ask questions, or you can always send me a question in the chat, and I'll try to interrupt Tung for you. But please go ahead and take it away, Tung.
Hi, everyone. Today I will talk about the presentation matrix, presentation-based metrics on merge trees. And this is the joint work with Justin Curry and Mike Lesnick and Robert Cardona from Albany. So to start, to get started with the talk, I first going to go through the introduction for the motivation and what kind of distance that we trying to work on here, and what is the background motivation for that. Then I will go through the merge trees as the categorical construction, and then we will define the presentation on merge tree and say a few properties from that about that distance. So am I still connecting?
It seems to be good. And of course, I'm seeing that the transcription really doesn't understand words like categorical. So if it's a distraction, I can always disable the transcription.
Yes, I think it's fun.
Okay.
I can't see the transcript from my side, so.
Okay. Perfect.
So to start with this, I think that first so from the last talk that we can see from Adeline Garin, that merge tree appears in neuroscience study, and here I show a dendrogram of some sort of hierarchical clustering of in a genetic study, which you can see that the form of merge trees appear here. And usually in other fields, merge tree can rise up at the topological summary of some scalar value function. So there is a need to define the distance or input in other words, can we metrize the space of merge tree. In literature, we know that there is here is a merge tree that rise from the scalar function, that you can take the upper level set of a function, and to obtain a merge tree look like this. And hang on, and a merge tree look like this one can be bracket into small branch, one small long branch and one short branch here. It's so to compare merge tree. To compare merge tree in literature, we have we know that there is a distance on merge tree, it's called interleaving distance, which means that Morozov and his co-author defined interleaving distance based on the pair of compatible map. That so that if you map from one merge tree, for example, the blue one here into the red one, and map back by another map, let's shift it just an epsilon, the diagram here is commutes, which means that the value of when you map from beta back, shift it in epsilon, and map it back by alpha, shift it in epsilon, is gonna coincide with the internal map to epsilon on the blue tree. So this distance has a benefit of being a matrix, which means it can distinguish two different merge trees. However, as shown by Yushu Wans and her co-author, that distance is NB complete, which means it's hard to compute. And even though it's hard to compute, it can be approximated. And it can be approximated by the bottleneck distance between the barcodes on the two matrices. So another advantages of this distance is that it's stable, which means that if you for the same topological space, and you have two different continuous functions, and you form a matrix by using the upper level set, then you have that the interleaving distance between two matrices can be upper bound by the norm, the infinity norm distance between two functions. So, so that is one distance that that motivates us to for our work today. Another distance that I will talk about is using cophenetic vectors on matrix to compare two matrices. So on a matrix with a fixed set of leaf nodes, we can label each of those nodes and then construct a vector that tells us how is the earliest time that two nodes merging. And that is the definition of a cophenetic vector. So for example, a cophenetic vector between upper trees with two nodes G1, G2, and G3 here. We have the cophenetic vector or in the form of vector or in the form of an upper triangular matrix. Tell us that the G1 gonna be appear at the time 1, and it's gonna merge with the G2 when it appears at time 3. One problem with this cophenetic vector is that it uses too much information, which means that for two matrices with n nodes, you need n time n minus 1 information on the matrix. However, if you look at the matrix, you only need you need n for n piece of information for the labels for the nodes, and n minus 1 piece of information for the time it merges. Another problem with this cophenetic vectors that you have in order to compare two cophenetic vectors together, the number of leaf nodes must be the same. However, we still can use the cophenetic vector to form a cophenetic distance between two matrices, which means that for two matrices with the same number of leaf nodes, we can stack. We can use the B norm on the difference of the cophenetic vector to give us the B cophenetic distance. This is the work done by Gabriel Cardona and his co-author. In the special case when B equal to infinity, the LP cophenetic distance here is a type of interleaving distance on label matrix. This is the work done by Lisman and her student. So the condition for the K when B equal to infinity, the condition of the fixed number of nodes and the condition of labeling can be relaxed by allow some sort of dummy nodes, dummy leaf nodes, and then consider on the permutation of labeling. In that case, Bjerkevik and her co-author show that if we do that, we can recover the interleaving on matrices. So we would like to provide a work that identify the interleaving on matrices the reason we want to do that is because the interleaving on mergery only is sensitive to the biggest difference and really insensitive to the smaller difference between two mergeries. And we can't do that with the definition by Morozov and his co-author. So what if we try to identify the distance based on the Cophenetic vector? The problem with the way of doing that is that the identified version of the Cophenetic vectors is not stable. Here is an example of the Cophenetic vector arise of two mergeries arise from the same cell complex with different value of function on that. Here we have the Cophenetic distance when the case p equal to 1 is 3. However, the distance between two functions f and g under the one norm is only 2. So
yeah, and Tung, can I just interrupt briefly?
Yes.
Yeah, so just so people are following along, normally when we think about LP distances on functions, we take the difference, take the absolute value, raise to the p power, and then we integrate the result. So here we're working with cellular monotone functions. So these are functions that are constant on cells in a cell complex. And so you can just kind of treat the function as like a vector, where on this cell it has this value, and on this cell it has this value. And so now you take LP difference between those vectors, and that's what we mean by the LP distance between two functions or cellular functions. And yeah, exactly.
So just like Justin said, the cellular function here gives us some sort of, we can see that function as a vector value, like the value of that function is in the form of a vector. It's not the LP function here. The LP norm here is not in the LP norm in the Lebesgue norm or something.
Yeah, very good. So I just wanted to clarify that for any analysts that we have in the room.
All right. So our work here was motivated by the works of Mike Lesnick and his co-author Harvard Bjerkevik on the LBT5, the distance on multiparameter of a system module. And we also build up on the idea that we saw in the cellular Wasserstein stability for persistent diagram of Skraba and Turner to provide the results on stability and universality for our distance. So first we revise a categorical definition for the mergery. The reason we're doing that because when we look at the interleaving on mergeries by the definition of Morozov and his co-author, there is a sense of things that can be described easily in the sense of functor. When you say that there's a compatible map and the diagram commute, all those things can be described way easier when you turn it into the categorical language. So first we give the definition of a certain set. A certain set is a functor from R into Z. And here we don't deal with persistent set in general. We just consider the persistent set that is constructible, which means that it's isomorphic to a left-hand extension of some embedded from N into Z along injective positive map J N into R. That's how we wrote it informally, but we think of that as the persistent set that have a chance that it just change at finite point. The chance in the persistent set just happens in a finite number of points in R. And usually we call it a critical points of the matrix. So with that language of persistent set, we define a matrix as a finite constructible persistent set where at some point on the branch merging, which means we have a condition that X with some R that big enough, it's just going to be one single skeleton. We give an example for a persistent set here. So we have the set that with one node at 0 and another node, another 2 points at the time 1, 3 points at time 2, and 2 points at time 3. And at the time 5, we have just one node. So because on the persistent set, we have to specify the morphism between them. So we said that all the morphism is going to be inclusions, except for the one between F2 and F3. We can, that's how we describe it in a formal term, but we can visualize as follow. Just one node at time 0, 2 nodes at time 1, 3 nodes at time 2, and 2 nodes at the time 3, and 1 node at the end times. And via Kant extension, it yields a matrix T, look like this one, which means it has 3 branches, one with the birth time 0, 2, and 1, and 2 of them merge at the time 3, and all of them merge together at the time 5. So as we mentioned, we want to take advantage of the categorical language here to define the persistent set because we want to make use of an interleaving distance. So we define the interleaving distance of a persistent set as follows. That's it. You can ship it an epsilon across from X to Y and ship it back another epsilon from Y into X. And then that must agree with the map from X into the internal map, ship everything to epsilon. And we define the interleaving distance on matrix M and N as the infimum of all the epsilon that you can shift in such a way. Our next step gonna be define some ingredients to cook up our presentations on matrix, which means here we look at a matrix with just one branch. It's gonna bond at some time and it's leave forever. Right. And all the morphism between 2 points on the matrix gonna be inclusion. So we just like describe the matrix with one branch. Now we describe the matrix with 2 branches. We can see the matrix with 2 branches at that you can glue those one branch together at some point. And in order to formalize that notion of gluing together, we use notion of co-equalizers here. So if you take F1, F0, and F1 at 2 branches to start with and glue it along F2, you're going to end up with a matrix that have 2 branches, one bond at 0, one bond at 1, and then all merge at 2. And we want to formalize this notion, not just for one single strand matrix like this one, but for every kind of matrix you can see. So the F2 here dictate the relation between F0 and F1. So we want to formalize in the form of generator and relation. Whereas one side you have a relation and it dictates how it's mapped into a generator and how it's glued together. So we need something look like this. So So we claim that all the matrix can be written in the form of relation integer generator via the co-equalizer and its yield material. And using that language, we define a representation of a matrix in the term of the co-equalizer that involve relation and generator. So here, for a representation of a matrix M, together with a given representation of with generators GIs and relation RJs, we have the following co-equalizer, and we call this one as a representation of M. So we give here is an example that we saw before, that a matrix with two leaf nodes born at time 0 and 1, and then both are merged at time 2. So the map F gonna dictate how you're gonna glue together. The relation into generator. However, the language of representation give us some sort of flexibility, which means that there's no such a thing that you can fix a number of generator and relation for as matrix. We provide here, we allow some sort of dummy strand. That's when it go through the co-equalizer, it's going to yield the same matrix. However, here we have a representation of two relations, and three generator, and it's yield the same matrix of two branch as we saw before, because FA just a dummy node, and it's going to merge into itself. To give us a clear picture of what I was talking about, this is the matrix that we saw before. This is the same matrix that will be this is going to be the same matrix if we push it through a co-equalizers. FA merged to F1 and it's collapsed there dummy strange.
Sorry, Tung. So can you back up? So I just want to recap for everyone who is listening. So you can take a presentation. Again, the presentation is going to say, I have a strand born at each height of a leaf node.
Yes.
And then that would give me a bunch of disconnected strands. But now
yes.
I want to glue the strands together
yes.
by whenever there's an internal node, I'm going to use another strand, and I'm going to say
yes.
that strand sits inside of these leaf strands, and then
yes.
the gluing process is going to help stitch this all together.
Yes.
But of course, presentations are not unique, because you can always take a strand and then have it born at a given time and then immediately kill it.
Yep.
And as long as you then glue that to some part of the existing tree, that should be
yes.
okay.
Yep.
All right. So yeah, no, I
yep.
just wanted to, sometimes repeating it helps, but you're doing a great job so far.
So, so after we have a presentation like this one, we have a number of generator and a number of relation. This is not enough. We have the next step is that there must be some form that to capture the relation between the generator and relation in the form that we can calculate or can doing numeric arithmetic things on that. So next step, we define a representation matrix. So really similar to so here a representation matrix gonna give us the information between the relation and the generator. We define a representation matrix with respect to a given representation is a labeled matrix, which means that on the I row going to be labeled by the generator GI, and the J is, sorry, this should be column. The J column must has label of the relation RJs, and not just the label, we also care about the entry of the matrix, which means that for any I and J entries, it's gonna be 1 if there is a connection between that relation and that generators, and otherwise it's 0. So the same matrix that I showed before, that to leave bound at times 0 and 1 and merge at time 2. So for the first representation, excuse me, the representation matrix gonna have the column label as the column label at the relation, which is F2, and the generator label as the F0 and F1, and both of them are related by F and G. So both of them related to F2 by F and G. So the entries here can be 1. We play the same game for the case we have 3 generators and 2 relations. So we have F2 related to F1 and F0. So the entry here is 1, 1. Fi related to itself at the degenerated generator, and F1. So the entry here is 1, 1. We know that even though that the representation is not unique in the sense of numbers of generator and relation, it's also not unique in the sense of the underlying matrix for the representation matrix. Here we have the 2 matrices represent the merge that really noted and pairwise merging at 2, 3, and 5, and they have the same generators, the same relation, but because of the merging functions are different, the underlying matrix or the associated representation matrix are different. Because of that, we define that 2 representations M and N are compatible if their representation matrix have the same underlying matrix. It must have the same underlying matrix, and which means that they not only required to have the same number of generator and relation, but also the merging must be somehow similar. Using this language, we define a label distance. First on, in order to define the label distance, we need to define a label vector, which means that for a given representation matrix, we got a label vector by taking on the row label and then stack it on top, and then we go after that by stacking on the column label after the all the row labels, and we don't care about F anymore. We just care about numeric values of that F. So using that, we define the label distance between 2 compatible representations as just a b-norm distance in the sense of b-norm of vector norm. Of vectors, sorry. So the same representation B M prime that have 2 matrix have with 2 branch that merge at time 2 is as follow, and then we make up the we get the label vector on that by stack on row, and then followed by on the numeric value of column. We do the same game for the merge with 3 branch that merge at the time 3 and the time 5 to have this label to have this label vector, and the label distance between those two gonna be here. Here the norm I use is the case p equal to 1. So we go through all of those constructions to define the presentation distance between 2p and m, which means that on we want to compare on the presentation that's compatible, and then we take the b label distance between their label vector, and we take the infimum on the possible compatible presentation between those two to form the b presentation distance between 2 merges. This definition is motivated by the presentation of multiparameter Persistent module in the works of Bjerkevik and Lesnick. So we define the distance like that, but the next thing we need to know is that when b equal to infinity, do we get back the interleaving distance, or it's just a completely new type distance? And luckily, we got the result that when b equal to infinity, the presentation distance gonna be the same cosine with the interleaving distance on merge. And not just that, when b from 1 to infinity, our distance actually form a pseudo matrix on merge, or we can say it is a matrix on merge modulo some isomorphic matrix. We provide a small corollary which is like trivial, that is, if you increase the b, you actually decrease the distance between those matrices. I understand this corollary is that when the b is small, the distance gonna be a little bit sensitive or shorter.
Sorry, Tung, can you go back? I just want to make a few comments just to summarize. And so, first of all, the presentation matrix between two for a merge tree doesn't immediately tell you the heights. So that's the one thing that already makes the presentation matrix different from the least common ancestor matrix, which is also known as the Cophenetic vector. But so the fact that you can take any two merge trees, and I guess we're assuming that there's a finite height for all the leaf nodes, and that they're always connected once you go up high enough.
Yes.
So it's it's a non-trivial thing to prove that you can come up with identical presentation matrices for both of them, right?
Yes, that's good.
And so, but trust us that we've checked that that's true. And now the way to actually measure a distance between two merge trees that look different, but they have the same presentation matrix, is we look at their label vectors, which are the heights of all these generators and relations. And then we just compute an LP distance difference between those two label vectors.
Yes.
And that is at least a number, but now we infimize overall possible compatible presentations. And eventually that defines theoretically a distance. It coincides with the interleaving distance when p equals infinity. And it gives us a new distance that changes when p is smaller than infinity.
Yes.
All right, perfect. Thank you.
Justin, I have a question.
Yeah.
Because the vectors associated with these merge trees are all finite dimensional vectors. So basically the metric are all equivalent.
Yes.
So for different P and Qs, you have this actually the equivalent metric. So what is the advantage you use P and Q instead of 2?
Right. Yeah. So essentially, there's always going to be some constant based on, let's say the length of the vector that makes all of these different norms equivalent. Part of it is, when we look at, say, machine learning applications, we want actual numbers out. And so it's not enough just to say that, well, they're all kind of equivalent. We want actually some of those numbers to help separate different data sets or merge trees. I would say from experience, when you look at p = 1, that tends to be a really popular choice when actually looking at applications, because it helps distinguish. It essentially treats all the little branches like on equal footing and totals up all of those differences. So it helps separate out merge trees that would normally be equal distance in the infinity norm. And then of course, you can kind of fine tune whatever your choice of P is to get something that helps separate out data sets. And typically P = 1 or 2 tends to be popular choices. Did that answer your question?
Yes, sure.
All right, great. But excellent question. But yeah, theoretically, these are all sort of equivalent norms. Yeah, and that's absolutely right. All right, Tung, continue.
All right. So, as we mentioned before that we can allow about interleaving distance by the bottleneck distance. The bottleneck distance had the huge advantages of commutable. So, but it has it also admits some sort of a generalization of that, but that bottleneck distance is called p-Wasserstein distance. So I give a definition of p-Wasserstein distance on the barcodes. Essentially, on the barcodes, we just see it as a bunch of intervals, and we identify each of those intervals with a point on R2, and we define a matching cost for each point. And the matching cost right now is going to depend on P, which means that we can tune the B to see that how much is going to be different. We can have two barcodes that the difference just happens on the long bar. So that's going to be seen by the distance when B equal to infinity, but not when B. That's going to be seen when B equal to less when B equals to 1, but not when B is equal to infinity. And we define the p-Wasserstein distance between the two barcodes by infimum over all the possible cost of matching like that. Here, the matching is just the partial projection from one to another. Together, by using one result in my paper, my Lesnick and Harvard Bjerkevik papers, we establish a law about our p distance. That's it. We can law about the b preparation distance between two merge by the b bottleneck distance on the associated barcodes. And I believe that this gives us some sort of a commutable sense for what we're trying to do, because right now I don't know if this distance is commutable. The b presentation distance is commutable or not. The next step, we're going to talk about the stability and universality. This part we bring up on the idea that we saw in Skraba and Turner papers on stability of cellular Wasserstein. They call it cellular Wasserstein stability, which means that let's recall that for the case of Morozov merge, we have that the interleaving is up about by the infinity norm between two functions on the same topological space. For our case, we can't consider a general topological space, so we restrict ourselves on the finite CW complex, which means on the finite CW complex, a function f is said to be monotone if the value on the cell going to be larger on the value on the face. And using the language of CW complex, we can define the B distance between the two pair of monotone cellular maps. Now it's just in the sense of a vector norm. By taking the value on each cell and stack it together to make a vector and take the B norm of the difference between two vectors.
Tung, can I interrupt briefly?
Yeah.
Yeah, so for those of you who haven't seen this, you might wonder, why do we have this monotone assumption on these functions? So one reason for that is if you take any real value t and you look at the sublevel set of a monotone function, this condition implies that the sublevel set is a subcomplex. And so, we want to make sure that we have like a full subcomplex so we can compute homology and things like this. And then that when we increase that real value, it's an inclusion of one subcomplex into another subcomplex.
Yes.
So that's the only reason why we have that assumption. Otherwise, things get a little weird.
Yeah, so we don't have a strange scenario that we have a node born now before the branch. So using that, under those assumptions, we show that we have some sort of an analog result to the interleaving stability. But for this case, it's gonna be for p presentation distance. That is that you can up about for the pair of cellular monotone function on the finite CW complex, and the p presentation distance between the associated barcodes, associated mergery, gonna be less than the p norm between the function. Here, the associated mergery is just like the upper level set mergery. And we go a little bit further by saying that we con the condition that we stay here, that every distance that satisfies this condition is a B stable distance. And we found that our distance is universal, which means that if you give another B stable distance, which we will have that B stable distance going to be the less sensitive compared with our presentation distance. And as a result, when we get the case when p equal to infinity, we have a corollary that the interleaving distance on mergery is universal. So that's the most of the result that cover in our work. For the future direction, we would like to know that the computability of the p presentation distance. We know that it coincides with interleaving distance when p equal to infinity. But for the finite case, when p equal to 1 or 2, we don't know if it's computable. It's like NP hard or NP complete or anything. And if it's NP complete, we would like to know that is there any way to approximate or any kind of fixed parameter tractable algorithm to compute. And because of the distance, the way we construct a distance, we would like to know that can we extend this construction for the case of riprap, and we would like to know that when we extend it to the case of riprap, what type of distance that we have for there? Does it coincide with any kind of distance that already exists on riprap? We're also interested to know that the LB type distance on persistence space, because on persistence space we already have the interleaving distance over there. Yeah. here is some reference that we used. The first one is the one that motivates like the LB distance on multiparameter Western motion, and a few other ones. Okay. All right, that's it. Thank you for listening.
Yeah, and thank you, Tung, for a really excellent talk. I'm going to go ahead and open up the floor to questions, any questions that people may have. So go ahead.
All right, so I have a question here. So there, earlier in the slides, you showed so given a merger tree, there's a presentation matrix, right?
Yes.
So, and the matrix may not be a square matrix, and
Yes.
it may include elements that are not necessarily 0 and 1, right? Yeah, so my question is that the
yeah.
presentation matrix.
Yes. Can I?
Yeah. So my question is, would matrix theory somehow help you to understand these merged trees?
Oh, that's pretty good.
Now, earlier in the slide, not only just here you have matrices only has 0 and 1s, but earlier you have matrices as other elements in it.
You mean the entry of the matrix? I think the entries of the matrix is just like 0 and 1. It just like recall that whether it's
earlier, even earlier.
You mean? Oh, you mean this one?
Yeah, that's right. Yeah, that's right. So yeah, something like that. Yeah. So my question is, will matrix theory somehow tells you more about this merged trees?
What do you mean the matrix series?
I mean, for instance, we can look at eigenvalues and the determinants, etc.
I haven't talked about that, but I don't know what is the determinant going to tell us. I'm not going to say anything about this matrix because it's a upper triangular. So the determinant going to be everything on the diagonal, if I remember correctly.
Why it is upper triangular? Why don't you make it a symmetric?
Because we try to get like a minimal information that we try to get the information as minimal as we need to. Otherwise, we have to like double everything. Like here, we just need to record where two strands gonna merge, and that's it first. So yeah, you definitely can get a symmetric matrix, but then you're gonna have to like you have the n square number of entries over there. Here's already the n times n minus 1 entries, and on a merge tree you only need n for the number of birth time, and then you have n branch. It's gonna merge at most at n minus point. So probably the number of pieces of information over just like 2n gonna be enough to describe a merge tree. So basically, we just pull out some sort of information as minimal as possible.
So I guess my question is probably just very general. It's how would the matrix help in the study here?
Well, and even Tung, even if the way that you currently store the information is in a minimal sense, like if the symmetric matrix makes sense from like a matrix theory perspective, it still could make sense to consider that other representation, even if it's not like a minimal one, you know, like yeah,
that's true.
Yeah, and I'll just point out to Ram. So this square matrix here is the least common ancestor matrix. So it is different than the presentation. But that said, like I don't know if anyone's considered like what are eigenvalues and and determinants of this matrix. It's an interesting question.
I don't think the determinant gonna give a good like symmetry or like invariant on that matrix, because you can cook up two matrices and then it merge it on the bond on a two leaf at 0, and then it's gonna merge at some point. Like if merged differently, then you're gonna end up in trouble that two matrix have the same determinant, but somehow it's represent two different merge trees. But yeah,
Well, it might be interesting to see which merge trees would give the same eigenvalues. If there'd be like a relationship present there.
yeah, that's true.
I think another question is, are there some operations on the merge trees that is corresponding to the product of matrices?
That is an interesting question.
That's true.
Yeah. Yeah, of course, you can imagine if you wanted to maybe glue two merge trees together at some common point, you could just take copies of their least common ancestor matrices and kind of include them as blocks inside of a bigger matrix, and maybe do things like that. But yeah, then what happens if you want to just do a naive matrix multiplication? Yeah, I have no idea.
So I don't know about naive matrix multiplication, but you can like shift entry-wise a little bit. So you end up with a merge tree that have range gonna move, like the merging point gonna move up until it's like epsilon ancestor. So that's one of the operations that I know for like operating on the matrices. But I'm not sure that if you multiply two matrices, what would you get now? That's an interesting question. I would try on some example to see that what will I get now if I do that.
Yeah, and I'll just mention, some of the generalizations of these ideas to the presentation matrix. Right now we have very simple attachments, so that's why everything's 0 or 1. But you might imagine that if you're attaching something with like a winding number, then you might want to encode that as like a degree in this matrix. And so this kind of gets at like, well, how do you present CW complexes that maybe aren't regular? Yeah, so that's another way in which like these entries might be interesting, at least from a topological perspective. Any other questions for Tung before we conclude? All right, well, if not, I'm gonna thank Tung again for giving a really great talk, and I'll see you all next week. So, all right, goodbye, everybody.
Thank you.